Cell 1. In this cell, we're laying the groundwork for developing a finance-focused language model. This is important because understanding financial texts, like 10K reports, earnings calls, and research notes, is crucial for accurately answering finance-related queries and executing specific tasks in this domain. We'll also introduce a robust workflow that ensures the model can effectively navigate the complexities of financial language. First, we need to focus on collecting and cleaning financial text. This step is pivotal, as the quality of our dataset directly influences the model's performance. After gathering the text, we'll move into building and tokenizing the dataset. The attention to detail here is essential because proper tokenization ensures that the model can effectively understand and process the language nuances that are specific to finance. Once we have our dataset ready, we'll transition into domain adaptation. This involves a continued pre-training phase that allows the model to better grasp the specific terminology and context found within financial documents. Following this, we'll instruction tune the model to ensure it can not only understand the language, but also follow complex financial instructions, such as summarizing risks or extracting guidance. It's also worth noting that we might implement a retrieval augmented generation approach for citing sources, enhancing the model's credibility. Evaluation will follow suit, where we'll measure performance using Perplexity as well as specific finance-related tasks to establish effectiveness. Finally, we can't overlook the importance of packaging the model for inference. This includes steps like quantization and making sure it's ready for deployment. As we look ahead, the next cell will likely dive deeper into the specifics of each of these stages, perhaps focusing on the intricacies of tokenization or the evaluation metrics we'll use. Understanding these components will be essential for building a reliable and efficient finance LLM. Cell 2. In this cell, we're setting up a framework to download recent financial filings from the U.S. Securities and Exchange Commission, specifically targeting key forms like the 10K and 10Q for selected companies. This is crucial for anyone interested in conducting financial analysis or staying informed about crucial corporate disclosures. To begin the process, we first establish the environment and necessary libraries. We import essential modules, including the SEC Edgar Downloader, which facilitates accessing the SEC's filings. Notably, we also suppress warnings here, ensuring that our workflow remains clear and focused. The next step involves defining the output directory where the downloaded filings will be saved. We create a folder named Finance Corpus, ensuring that the necessary directory structure exists, which helps maintain organization and accessibility of data. This is particularly important in data science, where managing files can become cumbersome without a thoughtful structure. Afterward, we set up a user agent. This is an important requirement from the SEC to identify users making requests, and it's advisable to use an email, a practice that also fosters accountability. Here, you would replace the example with your actual email to comply with SEC guidelines. Next, we identify the specific stocks we want to track, as well as the types of filings we're interested in. We've chosen popular companies, Apple, Microsoft, and JP Morgan Chase, along with the 10K and 10Q forms. This selection provides a strong starting point for gathering diverse financial data. Finally, we loop through each ticker and each form to download the most recent filings, limiting our downloads to 5 per form. This ensures that we aren't overwhelmed by data right off the bat, while still obtaining substantive information. The expected output at this stage will be a structured directory populated with the most recent filings for the specified companies, useful for any subsequent analysis. It's worth noting that while this process is automated, maintaining the integrity of the data and being cautious about potential rate limits from the SEC is essential. Looking ahead, we will likely move toward processing this downloaded data, allowing us to extract insights or generate summaries based on the filings we've just gathered. Cell 3. In this cell, we're taking a proactive step to evaluate our system's memory capacity before diving into a text analysis process. Understanding how much RAM we have available is crucial. especially since analyzing a large volume of text files can be resource-intensive. If we attempt this without sufficient memory, the process could crash, costing us valuable time and progress. We begin by retrieving the total amount of RAM on the system and then determine how much of that is currently available for our use. This is accomplished using the pseudo library, which provides handy functions to easily access system resources. The total memory gives us a sense of the overall capacity of our machine, while the available memory indicates what we can allocate to our analysis tasks right now. It's important to note that if the available memory isn't sufficient for our needs, we might need to pause for about 10 to 15 minutes to free up resources. This brings a level of practicality into our workflow. It helps prevent the system from crashing mid-process, which can lead to complications like losing our current state or having to restart from scratch. As we execute these commands, the expected output will be a clear indication of the total RAM and how much we still have at our disposal. It's a good practice to check this before embarking on memory-intensive operations, thereby avoiding potential pitfalls. In our next cell, we'll likely build on this foundation by determining our text processing requirements, which will help us understand if any adjustments or optimizations are necessary based on our memory assessment. This kind of precaution not only enhances our workflow, but also sets us up for a smoother analysis experience. Cell 4. In this cell, we're making a crucial step towards ensuring that our environment is properly configured for using PyTorch, which is fundamental for our project that involves deep learning. Checking that we have the right version of PyTorch installed is essential because it can significantly affect the functionality and performance of our models. To begin with, the code aims to import the PyTorch library as well as the system module, allowing us to access some important system-level information. By printing the executable path, we can confirm the Python environment that's currently running, which is particularly important if you're using multiple versions of Python. It helps ensure that we're using the intended one. Next, we print the version of PyTorch being used, providing clarity on whether it meets the requirements of our project. This is particularly critical because different versions of libraries can introduce breaking changes or deprecate certain functions, which might lead to unexpected behaviors. The third print statement reveals the file location of the PyTorch library itself. Knowing where the library resides helps with debugging and also gives insight into the environment setup, which can be pivotal when integrating various components or packages. It's worth noting that while these checks may seem straightforward, they are foundational. They help us avoid common pitfalls, such as attempting to use features that aren't available in older versions, or experiencing conflicts when multiple installations exist. As we move forward, the next cell will likely build on this foundation of understanding our environment by diving deeper into specific functionalities within PyTorch, setting us up to implement our first model. This preparation is critical when ensuring our learning journey progresses smoothly. Cell 5. In this cell, we're setting the stage for how we can efficiently access and organize filing documents from the SEC Edgar database. The goal here is to traverse the structured directory of SEC filings, pulling out relevant text files while filtering for quality and relevance, which enables us to create a structured dataset for further analysis. We start by defining the root directory where these filings are stored. The code acknowledges that SEC documents are not all straightforward text files. Instead, they are organized in a nested folder structure comprising various types of filings for different companies. The key to this process is the identification of specific file types that are deemed useful, listed in the candidate files set. This acts as our guiding list to prioritize which files to read when we find them within the nested directories. The heart of this logic is encapsulated in the iterFilingTexts function. As this function walks through the directory tree, it checks each item to ensure it's a file and matches our criteria of interest. We incorporate error handling to ensure robustness. If it encounters an issue while reading a file, it simply continues to the next without crashing. This is crucial since not every file is guaranteed to be readable or of good quality. A significant filtering step is also applied to reject any document that is shorter than a predefined minimum character count, as we want to avoid junk or incomplete entries. Furthermore, the function extracts the ticker symbol, which is usually found in the folder hierarchy. This information is vital for identifying which company a filing relates to. We also handle potential exceptions gracefully, assigning a generic, unknown label if the ticker can't be determined. By yielding a dictionary containing the text, file path, and ticker symbol for each valid document, we create a streamlined way to gather rich information from a potentially overwhelming amount of data. Finally, we gather these dictionaries into a list and convert that into a structured dataset, giving us a clear overview of how many documents we found and showcasing an example entry. Looking ahead, the next cell is likely to build on this dataset by performing deeper analysis, perhaps extracting insights or visualizing trends based on the filings we've gathered. This groundwork sets us up for some exciting explorations into company performance and regulatory compliance. Cell 6. In this cell, we're setting up a process to stream a specific dataset from a specified directory, targeting only the files that contain complete submissions. This approach not only optimizes our data loading, but also ensures we're working with cleaner data. The focus is on the full submission.txt files located within a designated directory that contains financial filings. The core of the function we're implementing is called gen full submission, which takes in a path to our data and specifies parameters for the maximum number of documents to process and the minimum character count for filtering. Within this function, we utilize a file traversal method that looks for every instance of full submission.txt through a recursive search in the given directory. For each detected file, the code reads the text content while taking care to handle any potential encoding issues to maintain the integrity of the data. To ensure relevancy, we perform a check on the text length, discarding any files that contain fewer than 2,000 characters. This ensures that we're only working with substantial submissions that are more likely to contain meaningful information. As we gather the content, we also extract metadata, namely the ticker symbol, which helps in categorizing the data. This symbol is derived from the relative path of the file, providing a clear identifier for our documents. The function yields back a structured dictionary containing the text, the file path, and the ticker, making it straightforward to utilize this output for further analysis. The count variable enforces a limit on how many documents are processed, keeping our dataset manageable without overwhelming resources. At the end of the execution, we create a dataset from this generator function and print it to get a glimpse of our processed data. It's important to be mindful of how many documents we're loading, as the limits set in our function help balance performance with data richness. In the next cell, we will likely delve deeper into analyzing this dataset, enhancing our understanding of the financial filings we've just streamed, and preparing for more complex analytical tasks. Cell 7. In this cell, we're setting up a key process for preparing our dataset for training a language model. This involves tokenization and reorganizing the text data into manageable formats. These steps are crucial because they ensure that our model can process the text efficiently during training. Initially, we're enabling a progress bar, which gives us feedback on how long our operations are taking. The code involves loading a specific tokenizer from a pre-trained model. This tokenizer turns raw text into a form that the model can understand, and we're making sure to handle padding correctly by setting a pad token if it's missing. Next, a function is defined to tokenize the examples from our dataset. This function leverages batching, which helps us manage resource consumption, particularly RAM. We specify a batch size that's small enough to avoid exceeding our system's limits. After tokenization, the text is removed from our dataset to streamline what we're working with. Following that, another function groups our tokenized text into blocks. This is vital, as it structures the data into fixed-size segments, which is necessary for training models like this one that expect input in a certain shape. We're particularly careful to maintain the overall size of these blocks. discarding any extra tokens that don't fit into our specified block size. After processing, we're creating a smaller version of our dataset for more efficient handling during experimentation. By selecting only a subset of the data, we can ensure that we're not overwhelmed during initial runs, making debugging and modifications more manageable. Finally, we're printing out some vital statistics about our tokenized dataset, including the number of rows. This insight is particularly helpful to understand how many training steps we can expect per epoch based on our chosen batch size. As we look to the next cell, we can anticipate that we'll be diving deeper into training configurations or perhaps even starting the training process itself, leveraging the structured data we've just prepared. This is where the real exploration into model performance begins, setting us up for exciting discoveries. Cell 8. In this cell, we're focusing on managing datasets through disk storage, which is crucial for efficiency and productivity, especially when working with large data. By saving our tokenized data and language model datasets to disk, we not only conserve memory, but also eliminate the need to redo work if we need to restart our session. The code begins by executing a couple of save operations. The toke.save-to-disk command is storing the tokenized dataset at a specific path on disk. This is vital, as it keeps our pre-processing work intact for future use. Similarly, the lmds.save-to-disk command is doing the same for our language model dataset, ensuring it's preserved and easily accessible later. Following the saves, we see the load from disk function being employed. This allows us to quickly retrieve the datasets when needed without starting from scratch. It's a straightforward yet powerful reminder that data persistence can significantly enhance our workflows. While utilizing these commands, one should be mindful of the paths specified. This means ensuring the directories exist and that you have appropriate permissions. If the paths are incorrect, or if there's an issue accessing the storage location, it could lead to errors. Also, be cautious about overwriting existing files when saving. Inadvertently doing so might lead to loss of previous work. By establishing this disk caching strategy, we're laying a solid foundation for upcoming analyses. In the next cell, we're likely to delve into how we utilize these datasets effectively, possibly applying some machine learning techniques or data manipulations that leverage the structures we just saved. This sets us up to maximize the efficiency of our processes further while building on the groundwork laid here. Cell 9. In this cell, we're setting up a training process for a language model using a smaller, CPU-friendly architecture. This is crucial because it allows us to handle resource limitations while still engaging in practical machine learning tasks, specifically fine-tuning a model on a financial dataset. The cell kicks off by ensuring that your environment is optimized for this operation, notably disabling parallel tokenization. This avoids unnecessary RAM usage, especially beneficial on CPU systems. We choose a manageable base model, the TinyLlama 1.1 billion, which strikes a balance between performance and computational efficiency. Alternatively, there's a larger model available, but given the constraints, sticking with the smaller option makes sense for now. Next, we load a previously prepared dataset that's stored on disk, specifically targeting a financial corpus to enhance the model's domain expertise. Notably, we're only training on a small subset of this dataset initially. Training on a manageable sample is a smart strategy, especially on CPUs, as it allows us to test the training setup without overwhelming our system. Following this, we initialize a tokenizer, ensuring that it has the necessary configurations, particularly defining a padding token if none exists, which is essential for handling model inputs correctly. Then we prepare our model, disabling the cache to prevent unnecessary memory usage during training. With this groundwork laid, we specify a configuration for the low-rank adaptation method, a popular approach for efficient fine-tuning that reduces the number of parameters needing updates. Throughout our training journey, we define important hyperparameters like batch size and learning rate. We've kept the batch size small and adjusted gradient accumulation to handle memory constraints. The max steps are deliberately kept low to avoid excessive resource usage while still allowing us to monitor the model's performance at intervals. The training arguments encapsulate all these settings, providing a structured way to train the model effectively. Finally, we kick off the training process with the selected model and dataset, utilizing the defined parameters and configurations. After training, the model and tokenizer are saved to a dedicated directory, ensuring that our work and enhancements are preserved for future use. Moving forward, we'll likely turn our attention to evaluating this model's performance and potentially making adjustments or further fine-tuning as needed. This iterative approach is key to crafting an effective language model tailored to our specific requirements. Cell 10. In this cell, we're set to test the performance of a language model designed to engage with finance-related queries. The workflow here is structured to utilize a pre-trained model and tokenizer for generating responses tailored to user questions, specifically about financial terms like the debt-to-equity ratio and EBITDA, which adds practical relevance to our exploration. First, the necessary libraries are imported, including PyTorch and components from the Transformers library, setting us up to leverage a specialized model. The base model we're using is TinyLlama, which has been fine-tuned, making it capable of generating nuanced responses. We also specify the directory where our model adapter is located, which contains additional fine-tuning for financial contexts. After initializing the tokenizer, an important step follows. If the tokenizer doesn't already have a padding token defined, we assign it to the end-of-sequence token. This is crucial because it ensures that the model understands how to handle inputs of varying lengths correctly, avoiding potential mishaps during tokenization. The main model is loaded alongside this adapter, which enhances its applicability to our topic. An important configuration adjustment is made, where we set the model's padding and end-of-sequence token IDs, allowing it to understand when to stop generating text. We transition into evaluation mode, signaling that we're ready to assess performance rather than train the model further. Next, we craft a user question and structure our input messages to include specific roles, a system message that defines the assistant as a finance tutor, and the user's question, all formatted for the model's context. This setup is vital for tailoring the output. Then, we tokenize the prompt to prepare it for generation, and finally, we use the model to produce an answer. Here, we carefully specify parameters for this generation, such as the number of tokens to produce and sampling strategies to enhance creativity while retaining coherence. The decoding step converts the model's output back into human-readable text. Finally, we print the generated text, revealing the model's response to our inquiry. As we proceed to the next cell, we'll likely dive into analyzing this response or fine-tuning our approach further, exploring how effectively the model responds to diverse finance-related topics. Cell 11. In this final cell, we're wrapping up our exploration of the project, signaling the completion of our analysis or computation. This is where we take a moment to reflect on everything we've accomplished, ensuring that we've covered all the necessary steps and produced our desired outcomes. As we conclude, it's important to think about the implications of our findings. By summarizing what we've done, we can reinforce the learning objectives and key insights gained throughout the notebook. This includes revisiting important variables that we have manipulated or analyzed in previous cells, drawing on the connections between them and the overarching themes of our work. What stands out here is the significance of clear communication of results. This part isn't just about completing the coding. It's about understanding how these results fit into a larger narrative. It's also essential to recognize any assumptions we made along the way, the choices that influenced our conclusions, and to be aware of any limitations that could affect interpretations. As we close this notebook, we prepare for the next stage in our journey. The upcoming sections will likely delve deeper into the analysis we've conducted, perhaps looking to apply further techniques or methodologies that enhance our understanding of the data. Getting ready for what lies ahead can inspire further curiosity and exploration in the analysis of our findings.